All right. So I back to the slide. I back to the page which you have already about the non-isolated statistical mechanics. The ensemble theory uh, which describe actually this system is canonical partition functions. And if you read it, the first few page, I think up to the page 11 or 12, then you see that then you saw that there you needed to I will share first. Okay. Then you will see that. Do you see my screen now?
Yes.
Yeah. You remember that we talked about the partition functions, and we said that if page 11, I think was, we saw
stopped
that,
at
yeah,
page.
if you say, yeah, 8 or 10, we say that if you have an energy, it is a question. If you have an energy levels for your system, you can calculate the partition function.
Yes.
But because the system is, we talk about the system with n particle, and actually this is a many body particle system, so for each energy level you can find maybe 10 copy or 100 copy of that in your system. So this is introduced to the concept we call it degeneracy. So degeneracy means that how many times one energy level is repeated. This is called degeneracy. For example, in hydrogen atom, the first level of energy is minus 13.6 electron volt, which is called S state, yes, S orbital.
Yes.
This is correspond to only when one wave functions. As you know, the wave function which the principal quantum number is 1, the orbital angular number is L is 0, and the azimuthal angular number M is 0. So this. But if you go to the second level, so second level of energy of hydrogen atom has a different energy. Do you know how much is the energy of second energy level of the hydrogen atom? Those are very basic questions and very important questions. I always ask anybody when I am talking, because as a student of physics, you have to, it's not enough to explain to people. You have to have the estimations of the numbers. Do you know how much is the energy of second energy level of hydrogen atom, second level?
No, I didn't remember.
And do you remember how the energy levels in hydrogen atom, for example, they are written? I mean, the first energy is minus 13.6, second is minus 3.9 electron volt. The next. So the energy level for hydrogen atoms, it comes like that. I have to open something here to write it, otherwise. So energy levels actually are given by minus 13.6 per n square of the hydrogen atom. So if you wanted to calculate, for example, the second energy level, so second energy level means just you set n2, so that you will see what is happening, and then you see that higher energy level, for example 6, it goes like this. 6. And what is important about, for example, this simple system is that when energy level is 2, so the wave function will be different. Wave function will be more than 1. So for n equal to 2, you can show that the L, which is angular momentums, will change from 0 to 1, and then the M, which is azimuthal angular momentum, will change also from 0 to +1 and -1. So you can now tell me that for example, for this energy level, how many possibility you have for a wave function. Wave function is a function of the coordinate and also is a, we write a PC, for example, it is given by the three quantum number n, l, and m. We know those from fundamental physics, from modern physics, yes?
Yes.
Wave function for. So if you fix n2, how many wave function you will get?
I think 6.
4. Huh? 4. One energy, one wave function will be the pair when you have 2, 0, 0. Huh? This is, we call it S2s orbital.
Yeah.
There is another possibility which you have 2, 1, 2, 1, and 0. Huh? What is the name of this orbital?
L. No.
2p. Huh? 2p. But 2p is not only 1. You can have 2, 1, 1. You can have 2, 1, minus 1. Huh? So here you can have 0, you can have 1, and you can have minus 1. This is a azimuth. So you have a 2p. 2p what? 2p1s, 2p1p, and 2p another orbital 2p. So you have a 4. So this possibility, which for one energy, you have 4 wave functions, one wave function and 3 wave function here. So totally you have 4 wave function. This is called degeneracy. Degeneracy. Huh? So just imagine this is about one particle. So if you have 10 particle, n is Avogadro number, 10 power 23. What's happened here? The things which happen here is that each energy level, which we call it E1, will be repeated with a large number of the factors. Huh? This is a degeneracy. This G here, you see.
Yeah.
In your case, in hydrogen atom, for example, degeneracy is 4, as you see. But when you have an n particle system, so degeneracy will be very complicated and will be function of the wave numbers, which we call it k. There are some example here. I told you how to calculate the partition function. The important fact is that to calculate the partition functions, you need the energy levels. But what we do if we don't have the energy levels? If you don't have energy levels, you have to go and use the phase space. The phase space description is another equivalent descriptions of any classical systems. If you have a classical systems which the momentum and momentum p and the coordinate q, for example, are related to each other like that, for each energy levels, for example, energy level E, here, E square over 2m is the kinetic energy, huh? And for example, any potential energy, let's call it V, for example, V as a function of Q. This is the conservation of energy, as you know. We don't have this for any system. Do you know which system has a conservation of energy? When you have conservation of energy?
At the closed system.
What? When?
Closed system, not open system.
What does it mean, open and closed? In classical mechanics, I mean, what is the conservation of energy? For example, if you're
That the potential and kinetic energy are conserved. The total energy does not.
it should comes with no. You should not. You should not explain this much more. When they ask you what is conservation of energy, you can say that as long as your potential is a function of the coordinate, or as long as your force is conservative force. If you are riding your car and if you have a friction force, for example, the friction force make your tire heated. You feel the heating in your tire. It means that the friction force, which convert to the heat energy, is not a conserved force. Conservation of energy is hold when you have a conservative force.
Yes.
As long as the potential is a function of coordinates, so you have a conservation of energy. So look, for example, this is the total energy of the particle with momentum P and potential Q. If I fix for you the mass, for example, forget about the mass, I set the mass 1, and if I fix the potential, for example, 1/2 Q, for example, and then I want to tell you that you can always plot, these equations. Plot what equation? This equation, you can plot it. You can plot for different energy. For different energy, you can plot it, this function of the relation between contour plot. You can always plot. For example, I have a system which the kinetic energy, potential energy is, for example, kinetic energy is P squared over 2. This is like half m P squared, or P squared over 2m. And potential energy, for example, is, as you see, for example, potential energy is Q squared over 2. Very simple. And momentum can change from any number to any number, and positions can change from any number. And you can plot these functions. As you see, this colorful plot gives you the relation between momentum in coordinates for different energy. For example, for energy of 20, you have this contour plot. For energy of 40, you have for energy 60 and whatever.
Yeah.
This is called contour plot. Contour plot is very useful when you want to find the partition functions. To find the partition function, you have to make integration over this space. This is called phase space. The horizontal axis is coordinate Q and vertical axis is P, the momentum. If you want to find the partition functions, you can use the contour plots and you can use the phase space partition functions. Look, for example, here the free particles in 3-dimensional has this as expression of the energy.
Yeah.
So to find the partition function, you need the energy because the particle is not quantized. So the momentum is free to have any numbers, as you see. And there is no potential here. So the partition function comes just from the kinetic part. When you have a kinetic energy, you just substitute this here. And because it's 3 dimensions, so you can divide this to the 3 integrals and make it one integral one by one. Each integral is the Gaussian integral, as you know. Then this expression gives you the partition function from free particle. Do you know why this h, the Planck constant, appear here with cubic for a particle? For free particle. Why you have h cubic? Why you don't have h2, h1, h5, h6?
Before we defined 3 momentum in 3 dimensions.
Yes, these 3 related to dimensions. And why you have a Planck? Why you have a Planck constant here? Because you know that the particle never can be classical, so P and Q are subjected to the uncertainty principle. Delta P, delta Q is always greater than or equal to half of the h. H is the Planck constant. So the minimum distance, the minimum volume or minimum area in the phase space in a statistical mechanics is not 1, is h. H is the Planck constant. This is what you have to read it before. I think you know something, or maybe you don't know. I don't know. That's the reason I review. So integration in the phase space is very, very important for us. when we go to economic physics, you will see that instead of the momentum, we have money. The currency trading in the market is called money. This works like a momentum. And what about the coordinate? Instead of the coordinate, you will see we have a partner or sharing. This money will be distributed over five sharing companies or 5 sharing partners. So it means that the coordinate Q is changing from 0, for example, to the 5.
Vector partners, we said before, is like are like the energy on the
Yeah, money works like energy also, because kinetic energy means energy. Yes. When I say momentum is money, it means that it's energy. But we have a budget. Budget is the total energy. You see, how much the total money or currency is trading in the market during the time. That gives you the budget of energy.
Yes.
For example, the maximum trading of the year in the one country is $1 billion, for example. This is the maximum trading rate or maximum trading operation which happened during 1 year in these trading markets. So this is a total energy. But you should not now think about that. This is very advanced. It comes next week. First, I want to see that how much physics you know, because before knowing all this concept, we cannot go there. This is very...
I start to revise the thermodynamic course, but I think these concepts are more in modern physics course.
Yeah, modern physics, because talking about the statistical physics, we are knowing the quantum mechanics is impossible. So knowing the modern physics and quantum mechanics is essential, actually, essentially, to know the statistical physics. That's the reason I ask you always, because I want to know that how much you remember about the modern physics or quantum mechanics. This is I know that quantum mechanics here is the course is very, very easy course, I know. So I don't expect that you know much information about that. But anyway, basic information is needed. So anyway, so there are so many examples. For example, you have a harmonic oscillator. There are some systems which their minimum energy is not 0, so they are called harmonic oscillators.
Yes,
Their energy levels is... Yeah, I asked you to drive this.
Yes.
So just briefly tell me how you do that, how you find the energy of the harmonic oscillator.
I write the Schrodinger equation.
Okay.
We have from the classical we know the potential energy and what is the kinetic energy. Then the second order differential equation we have. It's not easy to solve it, so
It is easy. People say it is not easy. It is easy. Oh, anyway. Okay.
Yeah, but I got back to the quantum mechanics course. We solve it that as we define non-commuting operators.
Annihilation and creation operators, yes.
Yeah. But we have other. Can I share you what I?
Yes. Maybe later, okay? When I finish this. Okay. Just briefly, I want to ask. So, okay, the partition function can be calculated 2 types. If you have an energy level, or if you have a phase space. This is what you have to remember. In economic physics and economical markets, the version which we use is the phase space. You have a phase space, and then you calculating by calculating the integral over the phase space, you can get the partition function. The thing that is important also in the markets is that fluctuations. So, for example, you have always things which call it inflations. So inflation is something which is related to the fluctuations. Price. How much the price is changing during the time when you fix the other parameter in your market. This is the things which we call it fluctuations. Fluctuation is also interpreted as a variance. Variance is the, you know that variance is given by the expectation value or average of the square of any parameter minus the square of the average. I mean, you measure that how much your data are far from the average, huh? This is, we call it variance.
Yeah.
And you know that several, in many places, you know where the variance comes. In the statistical physics, variance is very important because have some information about the variance, give you some information about the how much energy is transmitted or transported between the different parts of the system. To find the fluctuations, mainly we are talking about energy fluctuations in canonical systems. You need first to go and through and calculate the average of energy. Because everything is written in the notes, I just want to go very quickly. You need the average of energy, as you see, and you need the average of a square of the energy. Yeah?
Yeah.
If you have a partition functions, which is defined before, that was the partition functions. Partition function for one particle. Using the partition function, you can calculate any average. Mainly, you can calculate the average of energy, and also in terms of the partial derivative of the partition function, and also you can calculate the average of the square of the energy, which is written here. What is the physical interpretation of them? Physical interpretation of average of energy is that to find the average of energy, you need to have a list of the energies. Yes, energy 1, E2, E3, E4, and whatever. Each energy has a probability to appear in your system. Some of the energy appear with most chance than the other ones. For example, you know that in the physics, most of the system wanted to exist in the lower energy levels. So most of the times, the ground state, the state of the energy with lowest energy is the best. I mean, it has a great chance to appear in the system. Yeah.
Yeah.
So, and the other energy levels, no. For example, in the systems which you have a different energy level, like for example, you have a one electrovolt, for example, and you have something like 100 electrovolt and million. If you leave the system to itself, by itself, the system wanted to arrange the system in somehow that to get the minimum energy. Why this minimum energy is very important in physics, you know?
Minimum energy and the equilibrium.
For any system, what is important? For example, in news, you remember that always they said that we want to consume the budget. We want to reduce the budget. We want to reduce the budget. You know what is that? They want to minimize the energy. They want to minimize the money. Yeah. Why it's important?
Because when we find the equilibrium.
Yeah, because the system wanted to stay in equilibrium. Yeah. Out of equilibrium or non-equilibrium is very, very dangerous situation. Only in equilibrium you can have a peaceful environment for your system, or peaceful situation, and your temperature almost remains constant. So that is called the equilibrium or peaceful situation.
And then we can find the entropy.
Yeah, and then if you calculate the entropy, the entropy also wanted always to get the maximum. Maximum entropy is the best situation for the system, and minimum energy is the best situation for the system.
Yeah.
So to find the variance or to find the fluctuations, and I say that we are talking about fluctuation of energy, you are dealing with the derivative of partition function. You see all the derivation here one by one. The important thing is that after all, the ratio between the variance, I mean the energy fluctuation, the ratio between the energy fluctuation and the average energy will be proportional to the inverse of the n. Look. So because n is large number, so the fluctuation of energy will be very, very tiny number. So what does it mean? It means that don't worry to think about the average of energy. Average of energy will be like a total energy when the number of the particle is very large. Only one situation happens, and when the system undergoes a phase transitions. You are familiar with the phase transition. You know that the water is freezed, for example, and then if you set the ice cube outside, so it will vapor, and then it turns to the vapor, yeah? Or if melt first and then turns to the vapor, if you give them some heat. Such kind of the things is called phase transitions. The matter physically change. If it was before the solid, for example, it turns to the fluid, and then from the gases. So this is called phase transition. Only at the phase transition you should be careful about the variance of the energy and fluctuation. What is the phase transition? In economical markets, phase transition means economical crisis. When the economical crisis happens, the fluctuations will be high, 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 high. Yes? You need in some countries like Venezuela, for example, or I don't know, Egypt, for example. The inflation is 1,000, you see? As a person who, do you hear me?
Yes, I'm with you.
As a student who do this project, after that you will understand that when they say the fluctuation is high, what does it mean? Inflation high. Inflation high means that the fluctuation of the one quantity here is very, very high. It is rapidly changing, you see? And very highly changing. This is a fluctuation of the price, for example, there, or whatever. I want to tell you that when the inflation in the country is 1,000 or 2,000 or 400 or 300, it means that the system or the market is going to be in the phase transition. What is the phase transition here? It is a critical crisis. Okay? Everything back to the fluctuation. So if they give you a data of the price of the anything like a price of the bottle of water, for example, okay, during last 10 years, by looking at the change in the price, if the change of the price, if you calculate the variance you can calculate, yes, even by Excel you can calculate. If you calculate the variance, which we call here fluctuations of the price, which we call it here energy, if the fluctuation becomes very, very, very high, it means that the market is in the crisis. Do you have any question there?
No.
Okay. There are some examples which we are not interested to such example. They are really physical example, like the electrons. For example, this fluctuation can be used to estimate some information, to get some information about paramagnetism and those stuff. So we don't study that, okay? You can just pass from the example which they are about the electrons and those stuff. There is a concept we also have in the markets, we call it adiabatic change. What is the adiabatic change? Adiabatic means that the entropy slowly changing. And one other that is that the entropy should change very little. If the entropy change very little or not very quickly, then we call it that this change is adiabatic. Okay. but you don't have the idea about what is the entropy in markets, then we will talk later about that, because we have to, I told you, we have to explain the dictionary between the quantities before. But in real physical systems, the entropy can be calculated from the partition function. Again, if the change in the entropy is not very, very high, then we can say that the system is adiabatically undergoes phase transition. I mean, you know, crisis can happen or phase transition can happen in any system, yes? But it could happen soft or hard. For example, you can break some things just by one streak, or you can break it by 10. So if you break it slowly, finally it will break. But it is this change in the phase of matter comes slowly. Yes? But if you break it this one time, so the phase transition or crisis will happen one time suddenly. This is not adiabatic. Adiabatic means that do the change step by step. Okay? Here you will see some examples. All the things which we talk here, you can consider in the atomic system, in molecule system, and calculate the partition function. Those are far from our discussions. Also, we don't have something like quantization of energy in the markets. We don't have such that, because the budget comes like a money from 0 to million, for example, or something like that. The energy is spectrum of energy is continuous. It's not discrete. I mean, always between 1,000 and 1,001, there is a $1 change. So energy, or we can say the eigenvalues, or we can say the energy in the real systems are continuous. I mean the economical systems, markets. So quantization doesn't have sense to us. Anyway, but here you can see that, but in statistical physics, the particle can also be quantized. I mean the energy of the system can be quantized, as you know. Quantization means that the energy of system can have some special numbers, not any number. This is the example here, gives you the idea how to calculate the partition function if you have a discrete levels of the energy. There is a theorem also in statistical physics which is very important. It's called the equipartition theorem. Equipartition theorem say that in your physical system you have kinetic energy, you have potential energy, yes? Equipartition theorem say that under certain conditions, the expectation value or the average of the kinetic energy will be proportional to the average of the potential energy. Proportional. It could be equal, it could be half of that, or whatever. Equipartition theorem is based off the calculating the average of the kinetic energy. For example, look, this system, it's a harmonic oscillator. You have a kinetic energy, half of mx dot square, and you have a potential energy, as you see, half of kx square. Yeah. The average of the kinetic energy will equal to the potential energy under certain conditions. This is called the equipartition theorem. And because the total energy is potential plus kinetic, if I tell you that the potential energy has the same average as the kinetic energy, you can immediately tell me that the average of each of them is the half of the total energy. Yeah. So far, we talk about how to calculate the partition functions. Partition function will help you to find the averages. And finally, it gives you some idea about how much is the fluctuation of your quantity. In statistical physics, we are mainly interested in two types of the fluctuations. the fluctuation of energy and fluctuation of number of the particles. If your system is non-isolated, and if you are fixed at the temperature, your ensemble is canonical ensemble, then you don't have the fluctuation in the number, you have just fluctuation in the energy. But if you give the possibility to your system to also exchange the particles instead of the exchanging the energy altogether, then your system will be grand canonical. And this is the very open market if you want to compare again. As I mentioned, it looks like you should not only allow the import and export of the goods to your country, but also you allow the partner to come to you and you send the partner to them to do the business. Yeah?
Yeah.
Yes. So if you have a grand canonical, you can talk about the fluctuation of the n also. But in canonical, in our slide, we have fluctuation of energy only. There is another parameter which is important, and this parameter is the distribution of the momentum. I mean, if the momentum change between two numbers, how many of the state or how many of the possibility are existed between this interval from P1 to P2? How many physical state existed? This is called distribution or momentum distribution or velocity distribution, for example. And for most of the system in equilibrium, the distribution of momentum remain Gaussian. This is called Boltzmann distribution. If you think about the velocity like a price or money, the probability of the finding two tradings which they need almost same amount of the money is it's given by the some integration over the Maxwell distribution. So Maxwell distribution gives you these numbers. Number of the possibility which you have from one velocity to the other velocity. This is called velocity distribution or Boltzmann-Maxwell distribution. Boltzmann-Maxwell distribution is almost Gaussian, as you see. There is an average for these distributions. This is what you can find even in the physics holiday, chapter 21, I think. Gaussian distributions has important properties. So the first important characteristic property for that is that it has always average, and the average is 0. And second is that it has a variance, and the variance is proportional to the temperature. Of course, it depends. I mean, the velocity average is 0, but if you consider this in 3 dimensions, if you consider 1 dimensions, I mean, if in your trading markets you have just one type of currency, money is momentum, momentum is velocity, then the average of the money or average of the velocity will be proportional to root t, as you see here. And the variance will be proportional to the t, and then if you calculate the square of the v, average will be proportional to t, then the variance will be proportional to root t. To do the calculations in statistical mechanics, as long as you have the Gaussian distributions, you always are going to use the Gaussian distributions like what I see here. This is the Gaussian integrals, which gives you they gives you the moment of the different power of the x with respect to the Gaussian distributions. That was almost the things which I was expect you know from statistical mechanics. We have 20 minutes left, so I want to start very slowly about the Bosenstein condensations and what is the Bosenstein condensations. Do you have any question up to here?
No.
Okay. you see that at the wiki 2, we are still working on the concepts. So next week, we little go to the new words or new terminology. Okay. So Bose system. What is the boson? The bosons of the particle is one of the two type of the particle we have in the particle physics. Bosons are different from fermions. The things with the bosons is that the quantum mechanical wave function is always symmetric if the bosons change their place. The wave function of them remain always symmetric under exchange of the particle. If the boson 1 changes place with the boson 2, the wave function of the whole universe doesn't change, the whole system. As a student, what you understand from wave function? What is the wave function in quantum mechanics and modern physics? What information you can get from wave function?
We can get eigenvalue and the energy or state of the particle.
Wave. This is very formal, as you see. Say
the probability.
No. Yeah, probability. That the things which why we need wave function, because wave function is not physical function. Wave function could be complex number. And complex number, you cannot show me complex number in the real nature. You can show me no. Where is root minus 1? The complex number. There is no root minus 1. Huh? Yeah. There is no root minus 1. The complex numbers are just imaginary. So they are imaginary. So wave function is imaginary. I mean, for example, I defined wave function is, for example, exponential. This is a wave function minus, for example, x squared plus I multiplied to x. So this is the wave function. And then 2-dimension, x plus 1. For example, this is a wave function. This function doesn't have any meaning. It is just a solution of the Schrödinger equations, and that's all. It doesn't have any other interpretations. But if you, for example, go and plot this, for example, plot what? Plot the absolute of this, because you know that the wave function also doesn't have any meaning. Thing which has meaning is the absolute value of that. So this is the absolute value, and we let, for example, x to change like that and y change like that. Let's to plot this. This contour, which is very strange, and you don't see any real simple interpretation for the. Let me to add it one. For example, such contour. This is a psi square, So this is a distribution of the probability, with different positions at different positions. For example, you see that in this system, which we don't know what is the system, but we have, for example, wave function. This is our wave function here. If you have wave function, then by making the absolute of that, absolute square actually. Sorry. So that is square. You get the probability. So the place which is very, very dark has more probability. This is the final quantum mechanics. After all, you're talking about psi square. And using psi square, you can find the average of quantities. Average of x, average of momentum, energy, and so forth, whatever. Bosons are the system which the wave function is remain symmetric under exchange of the particles. This is the thing which I'm talking now is the chapter 7 of the book, which is the book is Statistical Mechanics Patria. I will send you the book. You can just, or I will send just this chapter, because the book is heavy. You don't need it. if you think still about the system which the number of the particles is very large, then the statistical mechanics of bosonic gas is very interesting. For example, the expression 1 and 2 gives you the pressure, volume, and number of the particles at the given energy for a bosonic system. Bosonic system, as any other systems, has a degeneracy. I mean, for each energy, you can find so many copies of that. So many parts of your system has the same energy. So you have something we call it degeneracy. Degeneracy of the energy for bosonic system is proportional to the root to a square of the E, root square of the E. I mean, if the energy increase, the degeneracy, I mean, the number of copies will increase also. With a large number of energy, it has a most chance to find several parts of the system with the same energy. So degeneracy will be proportional to the E power 1/2. When energy increase, there's increase. Using the degeneracy functions and inserting that in the expression 1, for example, you can get the pressure and you can find the number of particles per volume. In bosonic systems, you have several parameters. Macroscopic quantities for your system is still pressure, volume, temperature, yes, and total number of the particle n. The microscopic parameters which involved in the system are mass of the bosons. For example, this m you see is mass of the boson. You have h is the Planck constant, and you have a quantity which we call it fugacity. Fugacity is related to the chemical potential. You know what is the chemical potential? Chemical potential is the energy that comes by exchanging the number of the particles.
Yes.
Chemical energy, like what the name has, is like that. For example, in chemical reactions, because the number of the elements in the right and the left change, so kinetic potential energy, I mean the chemical potential energy will change. If your system is in equilibrium, you require that the chemical potential energy remain the same after and before the chemical reaction. In bosonic systems, to calculate the pressure, you need to evaluate some integrals. The integrals which given in the question 7 and 8, those are called Bosenstein functions. And those are very important functions. They are not the only ones. For example, I can show you one of my papers to you when I was studying the Bosenstein condensation, for example, in some systems. For example, in this paper, Bosenstein condensation, which I will explain, we are just talking about the Bose. So this is my paper. So Bosenstein condensation can happen for a wide range of the bosons. The bosons with the mass are a good candidate for a process of the Bosenstein condensation. But anyway, there are other models which, so for photons never happen. So I mean the photon, the boson should have mass. Calculating those integrals are not very easy. They are related to the Bosenstein function or Lerch functions. In the notes which I provided for you, you will see that in this chapter, you have to evaluate those integrals. And by evaluating those integrals, you can get the expression of pressure and the number of the particles. Do you know what is happening here? The things which happen here is that you have to exclude the energy levels of the the minimum energy level from the others. I mean, the scenario of bosons in the ground state, in the level which the energy is minimum, is different from the scenario of same bosons in any other energy levels upper than the ground state. Did you understand this statement?
Yes.
Yeah. For example, it looks like that person who's born in the poor family, for example, has a different destiny than the person who born in the rich family. Exactly. If the boson are in the ground state, if they have the budget, very little budget, their history or their scenario will be different from the ones which they are sitting the higher levels. So what does it mean? To calculate the integrals, you have to be very careful about the level of the energy when the energy is 0. You see, the ground state. Ground state is very strange. It has an energy level of 0. But unfortunately, when the energy of system tends to the 0, in a spatial range of temperature, the number of particles which are allowing to sit in the ground state will increase. What does it mean? You have for example, you want to go to the opera or concert, for example, and there is always two types of the tickets there, yeah, VIP and the usual tickets, yeah.
Yeah.
If the country be in crisis, financial crisis, what you expect? You expect the VIP tickets are selling more than the regular tickets or no? Of course, the regular tickets will be more sell to the people. Everybody wants to cheap, yeah?
Yeah.
So in a special case, in crisis, at the phase transition, at the Bosenstein condensation border, everybody wants to sit in the ground state and buy the lowest ticket, yeah? So you will deal with something very strange. The quality is low. Of course, the regular tickets are low quality, bad place. But there is a request from the market. Everybody wants these cheap things. What you understand? Understand that maybe 20% just will buy the VIP and 200 people will buy the regular tickets. So the number of the people who require the ground state N0 will be very, very, very large than any other N. Any other N, what does it mean? 300 persons want to sit in the concert. Only 20 of them are selling the VIP. The left of the people, 280 people person, wanted to sit in the ground state, the cheap tickets. That means that the system will go under the Bosenstein condensation. A cheap things in the market has more request. The number of people who buy the cheap things will be more large. You see, it's very interesting. So you will get something which looks like very useless, very cheap, but many people want that. So, but it never happens usually, It happens when the crisis is, when something strange happens in your system, When the money is not enough for everybody. That's true?
Yeah.
In Bosenstein condensation, we say that if the temperature goes down below special temperatures, which we call it critical temperatures, the things which happen is that the number of the particles which sit in the ground state will be very, very large number. So you will have a very dense state of the matter. It looks like you mix two fluids, and one of the fluid has very heavy density, like it's like mercury, for example, okay? The other one is water. The water is lighter than the mercury because it has a lower density. The mercury will occupy the whole cup. Most of the part of the system will be dominated by the mercury. So you will have something which very dense. One part of the system will be very dense. In Bosenstein condensation, this part of the system is ground state. I think by the example which I provide for you about the tickets, if somebody in future asks you what is about Bosenstein condensation and what is this business in the economy, you can easily say this example, okay? You will need this example when you want to do your first presentation. When they ask you, what is the business between Bosenstein and markets? You just tell them few words about Bosenstein. As I say, there is a boson, and some of the bosons want to sit in ground state when the temperature goes below, and then immediately give my example. You see the VIP ticket and the cheap ticket. When, not always, when the market is in the crisis. Okay? Yes, so if the temperature of the bosonic system, forget about the market, if the temperature of bosonic system goes below a special number, then the system will collapse. Phase transition will happen, and it is like a crisis. What does it mean when we say the temperature goes below a special temperature? It looks like that. We say that the inflation rate, for example, increase up to the large number, 2000, for example, then the crisis will happen. So if the market goes under crisis, the best market is for cheap things. If you bring some cheap things, you can sell to the people. Yeah? The cheap object, like, like, for example, in Corona. When the Corona started, so everybody needed the smartphones. Yeah?
Yes.
If you check at if you check the market, we're not talking about the iPhone and those stuff is expensive. You can see that most of the cheap smartphones which before nobody buy, now somebody will buy. So those companies earn a lot of money. Of course, also Apple earn a lot of money. But when the crisis started, the request for the lowest energy level is more than the request to sit in the higher energy level. All right. I want to stop here, but I will now send you this chapter. Okay. This chapter is very important for us. This is a chapter 192. Let me just see. Bosenstein. I want to. This project is not like the other project which people do. In other project, people, I don't know, they do some data analysis or something like that, or go to the experimental lab and do some measurement and make it a graph. This is the things which is you are dealing with the real life.
Yes.
And that will help you finally in future. Not this project. I mean, this type of the thinking. If you think about the world like a physical system, not always. Of course, for example, for Corona, COVID, for example, there is no physical model. I know. It is just about the people get sick and die. That's all. But this type of the thinking about the systems will help you finally. I'm sure. So I will send you the book. This not book, only this chapter. Okay, only this chapter. And then you have 1 week to read this also. Just go through that, and then again I will review this. I go from page to page just to see. But just stop sometimes on the equations and see what's going on in the equations. Then I think you already received it. Then I think next week we can slowly talking about the, I told you about the terminology, how this actually I share so many things now with you, so you have some idea about what is the relation. But to have a better idea, actually we need to sit one time again and repeat from there, something repeated, and talk about something from beginning.
Okay.
I hope that this 2 weeks experience with me is different. Actually, it is very different from what the other people do or talking. But I hope that it will be it make increasing your interest. That the physics is not just go to the lab or do some experiment or just sitting in a computer and writing the codes. I don't believe to it. I believe that physics is the theoretical physics you can do by just pen and pencil and or paper, you know. And the idea are great. Ideas should be great, actually. And then you can go to the lab and do the experiment and verify that. That was happening in quantum mechanics. You know, quantum mechanics start by paper first, and then people goes there and they make the experiment and say that's all. Okay, thank you. So if you have anything, just write me anytime.
Okay, thank you.
See, I will send you the share of this video. I will send you. Okay, see you.
Okay.
Goodbye. Goodbye.
Thank you.
Thank you. See you. Goodbye.